Zero-Valent Iron filtration. Not a filter medium, an electron donor. And the distinction matters the moment your water source stops being a tap. Metallic iron at oxidation state 0, Fe0, carries a strong thermodynamic drive to donate electrons to anything oxidized enough to accept them. Chlorinated solvents accept. Heavy metal cations accept. Nitrates accept. The iron corrodes. The contaminants are chemically converted or immobilized in situ. The system runs that reaction continuously, without a power input, without a chemical dosing schedule, and without any maintenance interval recognizable from conventional water treatment. The technique didn't originate in a forum. It came from groundwater remediation engineering in the late 1980s and early 1990s. Researchers solving industrial contamination plumes without excavating millions of tons of soil. They buried iron walls underground, let contaminated groundwater flow through, and monitored the chemistry running passively for years. The engineering term is permeable reactive barrier. The operational reality is a redox machine with no utility contract and no recurring cost. The distinction from every other treatment approach in this list, ZVI drives long-term reductive transformations that cannot be replicated by adsorption alone or by oxidative treatments. Your membrane removes. Your tablet kills on contact. Zero-valent iron chemically converts and continues converting for as long as reactive iron surface area remains. That persistence is the design feature that made it viable for large-scale remediation and that makes it viable for independent water management. If you're tracking which contaminant class maps to your local water source, comment below. The rest of this breakdown layers the second metal on top of this foundation, and the interactions compound considerably. What copper and silver do when dissolved into that same water column is a different threat model entirely. One that hospital engineers figured out half a century ago, and quietly kept off the consumer market. 8 purification levels in this breakdown. Zero-valent iron, copper-silver ionization, silver-ceramic, copper mesh, galvanic cells, Fenton catalysis, electrochemical electrodes, iron oxide sand, silver nanoparticles, copper oxide ceramic, portable galvanic kit, and the oldest dataset of all. The list runs from 1990s remediation engineering to pre-Roman empirical practice. Every entry is a separate system. Every entry solves a different contamination profile. None of them is a universal solution, and combining them without understanding the chemistry is how you create problems instead of solving them. Copper-silver ionization. I'll tell you where I landed on this after going through the data, because my initial read on it was wrong. And wrong reads in a grid-down situation have a specific kind of cost. The mechanism: copper and silver ions released at sub-ppm concentrations. Cu2+ at 0.2 to 0.8 ppm disrupts microbial cell membranes through electrochemical interference. Ag+ at 0.02 to 0.1 ppm denatures the proteins bacteria need to function. Neither ion depletes on a single pass through the water column. They persist, providing continuous disinfection rather than a one-time kill event. That persistence is what solved Legionella in hospital water systems when chlorine couldn't. Chlorine residual fails against established biofilm in recirculating pipe networks. The ions penetrate. Hospital engineers developed this method in the mid-20th century specifically because the centralized chlorination protocol had a structural blind spot, and the market never promoted a solution that made chemical dosing contracts redundant. Stay invisible. Full ionization protocol and dosing tables are in the description. The ceramic filter architecture that comes next took this same mechanism and made it entirely passive. No power source, no maintenance cycle, no consumable beyond the filter medium itself. Silver-impregnated ceramic filters. Architecture: porous ceramic matrix with silver ions bonded into the pore structure at the point of manufacture. Water moves through by gravity. Ag+ leaches from the ceramic surface at the water-ceramic interface and binds thiol groups in bacterial enzymes, shutting down metabolic function at the molecular level. Protozoa and suspended particulates are physically captured by the pore geometry, a dual-mode removal system operating simultaneously. Origin: household ceramic candle filters developed in the 19th century for domestic water treatment, refined with silver impregnation as a deliberate bactericidal upgrade. The baseline architecture predates every chemical treatment protocol the modern water industry currently sells at margin. The operational distinction is the combination of power independence and dual-mode action. Most bactericidal approaches require either continuous chemical input or electrical power. This one runs on gravity and the galvanic chemistry of silver already embedded in the ceramic body. At correct flow rates, Ag plus output in filtered water stays within WHO safety thresholds. That's engineered design, not improvised approximation. Hardened and ready means this is already in a functional kit. Drop a comment on what your current backup filtration stack looks like. The threat is worth it. The passive contact kill mechanism here relies on fixed silver in a ceramic matrix. What comes next removes the housing entirely and runs the same copper ionization with nothing but woven metal and water in contact. Copper mesh passive ionizers. Woven copper submerged in water. That's the system. No power source, no electronics. The only consumable is the metal surface itself. Surface corrosion at the copper-water interface continuously releases Cu2+ into the water column. Those ions attack microbial cell membranes through direct metal-ion binding. The reaction runs as long as copper and water are in contact. No dosing interval, no pH adjustment, no infrastructure dependency. Stay rational. Maritime engineers validated this empirically for centuries before anyone ran controlled trials. Copper hull sheathing on wooden ships controlled biological fouling because the ions were always present and always working. The mechanism wasn't discovered in a lab first. It was confirmed there later. The operational distinction is the failure architecture. Passive copper mesh has no failure mode other than physical depletion of the metal surface. No power source to lose, no chemical to run out of, no moving part to seize. That's the point, not a limitation. Pairing this passive copper surface with iron in the same water column converts steady-state ion release into an active electrochemical engine. What that pairing produces is not what either metal produces alone. Editor note, scenario card. At this transition, display an on-screen text card. Each system in this breakdown is a standalone solution. These are not meant to be combined in a single container. Match the system to your contamination profile and operational constraints. Bimetallic copper-iron galvanic cells. I built a test rig for this. 2 plates, 2 metals, 1 container of contaminated water during a local boil advisory. Expected additive chemistry got a self-driving oxidative process I hadn't fully accounted for. When copper and iron share an electrolyte, which is what contaminated water is, the electrochemical potential difference drives a microcurrent without any external power source. Iron corrodes as the anode, releasing Fe2+ and Fe3+. Copper acts as cathode, releasing Cu2+. That current generates localized oxidative species in the water column, capable of attacking organic contaminants and stressing microbial structures simultaneously. The origin is corrosion engineering and environmental remediation research, specifically the discovery that dissimilar metals in shared buried environments produce active oxidative chemistry, not just passive ion leaching or simple corrosion byproduct. The distinction from either metal operating alone. The galvanic potential difference is the power source. No external input, no grid required. Full build schematic in the description for anyone running this off-grid. What that iron-copper pair does when dissolved oxygen enters the water column is where the system stops being an ionizer and starts being a chemical reactor. And that mechanism is what the next block unpacks. Fenton-like iron catalysts. Counterintuitive fact. At sub-ppm concentrations, iron doesn't passively contaminate water, it catalyzes. Fe2+ reacts with dissolved oxygen or trace hydrogen peroxide, naturally present in source water, to generate hydroxyl radicals. OH. These are among the most oxidatively aggressive species in aqueous chemistry. They attack organic molecules without selectivity. Pharmaceuticals, pesticides, biotoxins, viral capsid proteins. The catalytic cycle sustains itself because copper in the same system accelerates the back reduction of Fe3+ to Fe2+, keeping the loop running as long as dissolved oxygen is available. This advanced oxidation pathway has been documented in wastewater treatment research since the mid-20th century. The engineering evidence is not ambiguous. The reason it didn't scale to standard municipal water treatment practice isn't an engineering failure, it's the economics of centralized chemical supply contracts. A system that generates powerful oxidants in situ from trace metals already present in the water doesn't require a supplier. Stay invisible. Operational distinction. No exotic reagents. The inputs are iron, copper, dissolved oxygen, and contact time, available without a utility contract or a supplier relationship. The next block adds dose control and switch-off capability to this same underlying chemistry. Electrochemical copper electrodes. Passive copper ionizes at whatever rate the water chemistry allows. A polarized plate lets you set the rate. Apply a small voltage to a copper electrode submerged in water, and you're running a precision ion source. Anodic polarization releases Cu2+ at a controlled, adjustable rate. At specific voltage ranges, the same electrode also generates hydrogen peroxide directly at the metal surface, a secondary oxidant produced in situ with no chemical input. Minimum viable build: copper plate, 9-volt power source, timer circuit. Full schematic in the description, including voltage thresholds for H2O2 generation onset. The distinction from passive copper: switch-off capability. You control the dose. You stop dosing when it isn't needed. In any grid-down scenario with residual power capacity, a solar panel, a vehicle battery, a hand-crank generator, this converts that resource into precision disinfection output. That's a force multiplier for any existing prep. What comes next handles the contaminant classes that ion chemistry alone doesn't fully resolve, and does it with a filter medium that doubles as a catalytic converter simultaneously. Iron oxide-coated sand filters. The first time I pulled apart the literature on this, I kept reading it as a standard adsorption medium. The mechanism runs deeper than that. Iron oxide-coated sand is a dual-action system. The ferric oxide surface adsorbs arsenic and certain organic compounds through electrostatic and ligand exchange mechanisms. That's the part most descriptions cover. What they underemphasize is that this same surface creates a redox environment that catalyzes the oxidation of dissolved iron and maintains conditions hostile to microbial colonization simultaneously. The medium was developed for municipal and point-of-use applications because it addresses mixed contamination profiles, chemical and biological, without continuous chemical input. The origin is field water treatment engineering targeting arsenic-affected groundwater in regions where centralized treatment was unavailable. Low maintenance combined with dual-mode removal is the operational distinction. Most filter media solve either the chemical problem or the particulate problem. Iron oxide-coated sand handles both. While the redox zone it sustains suppresses microbial growth, a function that pure adsorption media don't provide. Prepare in silence. Full column assembly specs and media sourcing are in the description. The nanoparticle variant in the next block takes the silver contact kill mechanism and packs it into a significantly higher surface area format, with trade-offs that matter for implementation. Silver nanoparticle coatings. High surface area is the variable that changes everything in contact kill chemistry, and nanoparticles represent the extreme end of that optimization. Standard silver ions leach from a surface at a rate determined by that surface's exposed geometry. Silver nanoparticles maximize surface area per unit mass by several orders of magnitude. The result is accelerated Ag+ delivery and dramatically increased reactive oxygen species generation at the particle-water interface. Contact killing efficiency rises. Pathogen inactivation time drops. The trade-off is precision. Higher Ag+ leaching rates raise ecotoxicity concerns in discharge water and attract regulatory scrutiny that fixed ceramic silver doesn't. Editor note: technical alert graphic on screen. A nanoparticle coating on filter media must be chemically bonded to the substrate, not surface applied, to prevent uncontrolled silver release. The engineering distinction between a bonded nanoparticle coating and surface dusted silver is the difference between a functional field system and an ecotoxicity liability. This category is under active regulatory review in most jurisdictions. The mechanism is sound. The implementation requires design discipline that commercial off-the-shelf solutions don't consistently exercise. Full specification review in the description for anyone building independent filtration infrastructure. The copper oxide ceramic variant that follows solves a different engineering problem: operational life in harsh physical environments where organic-based filter media degrade. Copper oxide ceramic media. Most organic-based filter materials have an environmental failure threshold: temperature extremes, UV exposure, chemical incompatibility. QO-impregnated ceramics are designed for the operating conditions where those materials stop working. Ceramic porosity physically captures particulates above a defined pore size. Same physical mechanism as silver-impregnated ceramic. Different active dopant. QO surfaces catalyze redox conversions at the ceramic-water interface and release Cu2+ on contact throughout the filter depth, providing simultaneous chemical disinfection during filtration. The ceramic matrix is thermally stable across the temperature ranges that destroy polymer-based media, and the copper oxide dopant doesn't leach at elevated temperatures or degrade from UV exposure. The origin is harsh environment water treatment engineering, applications where conditions that destroy softer materials are baseline conditions, not edge cases. Stay invisible. The operational distinction is service life. Organic resin filter media degrade through chemical saturation and physical breakdown at predictable rates. QO ceramic media don't have a comparable failure timeline under normal operating conditions. In any scenario where resupply is uncertain or impossible, extended operational life without performance degradation is not a minor variable. It's the primary design constraint. Full media sourcing and column configuration specs are in the description. The portable field assembly in the next block takes copper and iron and builds them into a kit that anyone can operate without prior engineering background. Portable galvanic water kit. I put together a version of this for a road trip through an area with aging municipal water infrastructure. Not a wilderness situation, an urban one, because urban water systems fail in ways that are less predictable and less visible than surface water contamination. The assembly: a copper plate, an iron plate, a gravity-fed ceramic pre-filter, a sealed output container. Galvanic chemistry between the plates drives ionic disinfection and generates localized oxidative species without any external power input. The ceramic pre-filter handles particulates and provides a silver-based bactericidal layer before water reaches the galvanic stage. The sealed container prevents recontamination after treatment. The mechanism is the same galvanic redox coupling we've covered, packaged for field deployment by someone who is not a water treatment engineer and may not become one. Low-skill deployment was a design constraint. The technology originated in humanitarian field engineering and DIY resiliency communities, building potable water access for post-disaster environments where centralized infrastructure had failed and professional expertise wasn't available. The operational distinction: off-grid reliability without specialized knowledge, no calibration, no chemical consumables, no power source. Full assembly guide and component sourcing list are in the description. What this kit demonstrates practically is the same conclusion the historical record reached centuries before modern water chemistry existed. And the final entry documents exactly where that empirical evidence starts and how far it goes. Silver coin distillation practice. The oldest validated dataset on metal-ion water preservation isn't in a peer-reviewed journal. It's in recorded history. Silver coins placed in water storage vessels, silver plates lining containers, silver-lined drinking cups in Persian and Greek households. These were empirical experiments conducted over centuries, validated by differential survival outcomes between populations that used them and populations that didn't. The mechanism: slow Ag+ leaching from the metal surface at concentrations low enough to avoid acute toxicity and high enough to maintain bacteriostatic conditions. Microbial load suppressed, not sterile by modern standards, functional by any pre-industrial survival standard. The historical record includes documented observations from Persian military campaigns. Commanders transporting water in silver vessels reported fewer waterborne illness casualties than those using clay or wooden storage. Alexander the Great's supply logistics included silver containers for drinking water. The empirical observation predated the chemical mechanism by roughly 2,000 years. The physics hasn't changed. Ag+ still binds thiol groups. It still denatures bacterial enzymes. A pre-1965 US dime contains approximately 2.25 grams of silver, sufficient to treat a 1-liter container to bacteriostatic Ag+ levels within 24 hours of contact time. That's not folk medicine. That's inorganic chemistry running on a coin. Stay rational. And understand what this endpoint reveals about everything covered in this list. 2 metals, operating through electrochemical principles documented for millennia, have been solving the potable water problem longer than industrial water treatment has existed. The centralized protocol has a 50-year track record. The metal-ion approach has a 2,000-year track record. The protocol's specifications and field assembly guides for every system in this breakdown are in the description. Implement what fits your threat model. The grid will not always be available to make that decision for you.